All right, welcome everyone to the AI Research Roundup. I'm Alex. Today, we're looking at FastVLM, Efficient Vision Encoding for Vision Language Models from December 2024. This paper introduces a way to make vision language models, AIs that process both images and text, much faster. It presents FastViTHD, a new vision encoder, which is the part that handles the visual input. This encoder reduces processing delay, or latency, and uses fewer visual tokens, small pieces of image data, for high-resolution images, simply by scaling the image. This really speeds up the time to first token, which is how quickly the model starts responding, and simplifies the design. And it's great to see they've also released the code for this work. So on their GitHub repository, you can find the core implementation, how they built FastViTHD, along with pre-trained models and scripts to run predictions. They even have details for an iOS demo and exporting models for Apple Silicon. Okay, so this first figure 1, really visualizes how FastVLM, specifically its FastViTHD vision encoder, stacks up against previous methods. We're looking at two graphs here, showing accuracy on the vertical axis against that, quote, time to first token we talked about on the horizontal axis, which is how quickly the model starts generating a response. Lower time is better, and higher accuracy is better. The blue line, representing FastViTHD, consistently sits in that sweet spot, high accuracy with a faster response time for both the QN2 and Vicuna 7B large language models shown. Alright, this table here, Table 1, gives us a closer look at the performance of an earlier version, called FastVit, compared to a standard vision transformer, or VITL/14. A vision transformer, well, it's a popular type of AI model that processes images by, essentially, breaking them into smaller patches and analyzing them. So, looking at the numbers, FastVit, even when handling a higher resolution image at 768 pixels, gets a better average score, 62.6 compared to 61.2 for the vision transformer, and impressively, its vision encoding latency, that processing delay we talked about, is down to just 34.5 milliseconds from 127.4. That's significantly faster. Okay, so figure 2 gives us a nice overview of the entire FastVLM architecture. On the left, we see the FastViTHD vision encoder. An image goes in, and it's processed through several stages. It starts with a convolutional stem. That's an initial processing layer using convolutions, which are good at picking up basic visual patterns. Then it moves through what they call rep mixer stages and patch embedding stages. These are designed to efficiently process the image information. Later stages use self-attention layers, which help the model focus on the most relevant parts of the image. Notice the learned pool blocks. These help to downsample, or reduce the size of, the image representation at different points. This multi-scale information is then combined and projected before being fed into the large language model. Meanwhile, any text input, like a question, goes through a tokenizer, breaking it into pieces the model understands, and then also to the large language model, which finally generates an answer. This design, with its specific stages and downsampling, is key to how FastViTHD generates fewer visual tokens and achieves that low latency we discussed. Now, Table 2 delves a bit deeper into how they refined the earlier FastVit model, which is the predecessor to FastViTHD. It looks at using multi-scale features. That's where the model looks at the image at different levels of detail, like we saw with the various stages in Figure 2, and different pooling strategies. Pooling, remember, is how the model summarizes and reduces the image information. They tested AVGAY-pool, which is short for average pooling, a method that takes the average value from a small area, and DW-conv, which stands for depthwise convolution, another way to process features. The results show slight improvements in the AVG5 score. That's an average performance across 5 different benchmarks, particularly when using multi-scale features with DW-conv. Alright, Figure 3 here really drives home how FastViTHD's design helps with speed. We're looking at latency in milliseconds on the vertical axis. And note, this is a log scale, meaning the visual gaps actually represent even larger differences in processing speed. Again, lower latency is better, On the horizontal axis, we have image resolution in pixels, going from 256 up to 1024. The blue line, representing our FastViTHD, stays significantly lower than both the orange line for a naively scaled FastVit and the green line for ConvNextL, which is another type of vision model architecture provided here for reference. What's really telling is that FastViTHD achieves this lower latency while having the same number of parameters, those internal model settings, as the naively scaled FastVid. This clearly shows FastViTHD's novel scaling strategy keeps that processing delay down effectively, even as the image resolution gets higher. Okay, so building on that, Figure 5 now breaks down FastVLM's overall speed, specifically looking at the time to first token. This is the total time it takes from when the model gets the image and text to when it starts generating the very first piece of its response. We're still seeing latency in milliseconds on that log scale vertical axis, and input image resolution on the horizontal. The orange bars show the vision latency from FastViTHD, and the blue bars show the large language model pre-filling time. That's the language model getting ready. Notice how at lower resolutions, the large language model pre-filling is a bigger chunk, but as resolution climbs, that orange vision latency really starts to dominate the total time. This shows just how critical an efficient vision encoder becomes for high-resolution inputs. So we've seen how the vision encoder impacts the overall speed. Now, Figure 4 takes this a step further by directly comparing the efficiency of FastViTHD, our new encoder, against its predecessor, FastVit. This chart shows what are called Pareto optimal curves. Think of these curves as showing the best possible balance between accuracy on the vertical axis, measured by that AVG5 VLM evil score, and the time to first token on the horizontal axis, which is again on a log scale. A better curve is higher up and further to the left, meaning higher accuracy for a given speed, or faster speed for a given accuracy. The blue shaded area and lines represent FastViTHD, while the orange ones are for the older FastVit. Each point on these lines corresponds to different image resolutions and various sizes of the QN2 large language model. It's quite clear that FastViTHD offers a much better trade-off. For example, the paper notes that for a given runtime budget, FastViTHD achieves over 2.5 points higher performance on that AVG5 score, or it can reach a target performance up to 3 times faster. This really highlights the significant efficiency gains with FastViTHD. As we've seen, especially with those Pareto optimal curves, FastViTHD really pushes the boundaries of efficient vision encoding. The key takeaway here is that by optimizing how these models see, we can get much faster responses from vision language models without sacrificing accuracy, particularly when dealing with high-resolution images. This is super important for making these powerful AI tools more practical for everyday use. Well, that's all the time we have for today's AI Research Roundup. Thanks for tuning in. I'm Alex.